10,000, and so on and so forth. So this is a redshift slice from the CFA survey, which was the first one that really mapped the galaxy distribution near us. Okay, this was in 1986. And what you see, it is not homogeneous and isotropic, right? So you see the stick man, see a lot of structure, that's what he was called. I don't know why it was a he actually, that's a good point. Yeah, whatever. And this is where it's at now. So, okay, so that slice that I showed you sort of fits here, okay, one time. So this is a very large redshift survey, and I'm purposely showing you the European British one and not the American one. There's an equivalent American one called SDSS. This is the 2DF redshift survey. It's, you know, my part loyalty to the UK. There's sort of two complementary surveys. So what you see here, this is the galaxy distribution. Okay, so what you see at each point here is the location in space and the location in terms of the recession velocity from us for a galaxy. And so what we have in the observation, so this is very rich observational data, and what can we get out of this? What we can get out of this are characteristic statistical distributions, statistics that describe this distribution of galaxies. Okay, so that's what we're getting out of redshift surveys. So if you've heard cosmologists going on and on about why they need larger and larger redshift surveys, it's because you ideally want to be able to test homogeneity and isotropy. You want to keep going further out to see, is there a scale at which the cosmological principle is going to be totally valid. It turns out, as far as we have seen, we see a lot of inhomogeneity. And you actually see not just galaxies clustered, so they're clustered, their locations are clustered, and their clustering can be understood as a result of gravitational stability and gravitational forces. But there are also these large regions which are called voids where you don't have any galaxies. But by and large, it looks like, at least the hope is, as we extend out and there's a lot of future, we can collect light only out to there. Okay? So all the data that I'm talking about is, yes, there's a backdrop of this, but the images and the clustering and the statistics we're talking about is from a very, very small. And so hopefully the next generation of technologies will inch us slightly further out. But, you know, it's not going to be there, not for a long, long time. So, you know, the region from within which we are going to get data that we can actually use to characterize and constrain this model is growing, but very, very slowly. Okay, it's growing dramatically in terms of the numbers. Okay, so let me now quickly give you a timeline of how structure formation works. Now I'll give you a sense of what is actually observed. So the cosmic microwave background constrains the very early universe, so it allows you to connect the temperature and density of the universe and the evolution of the temperature and the density. And basically I'll show you very quickly, maybe I'll skip through some of the slides, but you know, a day in the life of a density perturbation, how it works, okay? And then I will talk a little bit about the statistical description of structures and what we actually use. So what we really derive is a power spectrum of fluctuations. So it's the amplitude of fluctuations as a function of scale of those fluctuations. The theory predicts that. That's what we can compare to. Okay? And then I will move on to actually showing you some results from simulations. Okay. So basically, this is a basic component of the Big Bang model. It's reasonably well constrained observationally. As I said, modular relation between mass and light. So if you suspend belief for the moment and say, okay, it's only dark matter in the universe, let's worry about baryons later, then we have a very good working model. Okay? And it's very sensitive to, of course, the statistics of what the distribution of matter in the universe is. So now I'm switching to matter. When I say matter, we're talking about simulations. When I say galaxies, we're talking about the observations, right? So, and you know, the nature of dark matter has very important consequential statistical differences it produces in what you'll see in a simulation. So basically, gravity amplifies these inhomogeneities in the density field, even in an expanding universe. So you can think of it, I'll just quickly go through these. I mean, I'll make a PowerPoint available for anyone who wants to spend more time. So basically, you have these fluctuations as a function of time. They're growing and their sizes are growing in the universe. And you calculate the fluctuations on all scales, and their relative amplitudes of the fluctuations on all scales is described by this quantity called the power spectrum. which is the prediction of the model. The prediction of the model of any cosmological structure formation model is its power spectrum. Okay? And the evolution of these fluctuations to form detailed large-scale structure, you need simulations to study them because it's a highly complex problem involving many, many bodies. So the current paradigm, the cold dark matter paradigm, the buildup of structure is hierarchical, and you have, okay, so this, I just want you to focus, don't worry about the words, just focus here. So this is just showing you, so this is the density field of dark matter. So these are fluctuations, if you will. You think of dark matter as some kind of sheet with some fluctuations initially. And there are fluctuations on all scales, which is hard to draw and show. But so for example, this is an example where you have structure on two, fluctuations on two scales. So you see this large scale fluctuation, and on top of it, writing, you see these small scale fluctuations. So it turns out these fluctuations grow in time, and then when a fluctuation reaches a threshold, which is calculable, and that threshold is this red line, the matter that is here in these regions will separate out from the expansion of the universe. Its own gravity is going to be strong. The gravity of the stuff, of the matter, the dark matter in this lump, is strong enough to separate out from the expansion of the universe. And this little piece evolves from then on its own. So the Milky Way, the reason why you and I are not expanding, accelerating away from each other as I am speaking right now, is because the Milky Way is one such collapsed object. It has separated out from the larger expansion of the universe. So in order to measure the expansion of the universe, I need to make observations outside the Milky Way. Okay? So I need to see other galaxies that are receding away from us. No star in the Milky Way will carry any imprint of the expanding universe, okay? Because it's collapsed already under its own gravity. So we have a set of initial conditions that are well defined and constrained by these observations of the isotropy of the microwave background and the level of fluctuations. So then we can propagate them and link them.
And the threshold is determined by observation, or
no, theoretical.
It's a model.
It's a model. So maybe yeah, so basically the power spectrum. So what I want you to take away from here is that the power spectrum is the key prediction. Just to give you a visual sense, okay, don't worry about the words, the visual sense is that these images, so what I have, I'm showing you Fourier transforms of, so what I've done is I've set up an intensity field, I've set up brightness, and I'm putting in fluctuations of different scales. So it's the same image, okay, so there's the same background image on which I've put fluctuations on different length scales, and shows you that the granularity, the statistics of the bright patches. So if I want to look at how many bright patches are near other bright patches, what is the nearest neighbor distance to a bright patch from a given one, that's very different in each of these, right? In the universe, you actually have fluctuations on all scales happening at the same time. So there's a lot of rich statistical data. So that's what I want to sort of impress upon you. There's a lot of rich statistical data. Okay? And this is a further one, where basically I've now put in fluctuations on slightly different scales, and you can see visually these maps are all different. Okay? And when I talk about discriminating a model, the discrimination is going to come from measuring differences in statistics for final simulation slices that are going to look like this, or a combination of these. Well, it will become clearer when I actually show you the slides. So it turns out that the initial power spectrum, so the way a Mach power spectrum, so the initial conditions looks like this. With evolution, this shape is going to get modified. Okay? And that's what we measure. We measure things as they're as we see them today. So we need to evolve these density perturbations using gravity. Gravity itself is not complicated. However, with these many bodies that we have to consider, there's no way out but to do a simulation. So basically, we do simulations. So what do we do in a simulation? You model matter in the universe as a collection of particles that interact gravitationally. So I want to point out that we don't know what, I've told you that dark matter particles have mass. We actually don't know what their mass is. We know they have mass, but we have no idea what the mass is. Okay? So any particle that I'm going to show you in a simulation is going to be an aggregate of a huge number of dark matter particles.